All right, good morning everyone. I know we're all a little bit rowdy after our little morning tea break. So my name is James Mitchell and I work for Sledgehammer Games in Melbourne. Welcome to my talk on the operating system scheduler and your threads. The hardware and operating system landscape that we ship our games on is big. We need to consider desktop PCs, servers, consoles, mobile devices and more. Some of these devices might be super high-powered computers with multiple CPU cores. Others might be low-powered with a mixture of performance and power-efficient cores. Some might support simultaneous multi-threading or hyper-threading, and others might not. You might even have situations where you have multiple physical CPUs that you're dealing with. The operating system typically works with processors, each having their own threads, and virtual memory mappings which all of the threads use. These virtual memory mappings get mapped out into physical memory. Each thread also has its own unique instruction pointer that points to the currently executing instruction, and also its own set of registers. There's also a user stack where all of the local variables tend to get placed. And there's also a kernel stack whenever that specific thread wants to call out into the kernel. The operating system works with all of these threads, placing them onto CPU cores. So let's dig into some basic schedule operations. There are three main places or states which a thread can be in. The first one is the ready state, where it is placed into a queue ready to be moved into a running state. From that running state, it can also move into the waiting state. The waiting state is when it is blocked on some event, waiting on some event to occur, which could be waiting for data to be read from a disk, waiting for another thread to release a mutex, or any other event. However, when it is ready to go back to running, other threads might already be already running or already be in the ready queue. Threads moving from a waiting state can be added to the ready queue, or they can preempt the currently running thread, pushing it onto the front of the ready queue. These operations are the core part of every operating system scheduler. Let's look at some more basic schedulers. First up, we have the first in, first out scheduler, or the FIFO scheduler. Each thread has a priority which is specified by the application. The highest priority thread always runs. Only when the current running thread blocks will it be removed from the queue. Aside from blocking, a thread may decide to voluntarily switch or yield to other threads, which will move it to the back of the priority queue, and the next thread in the queue will start running. As only the highest priority threads will run, if there is a mixture of threads at different priority levels, then those high priority threads need to enter a waiting state before the lower priority threads are able to run. So here we can see these threads start to move out and start running. Each of them will start blocking, and then finally the lower priority thread will get its turn. The round robin schedule is very similar to the first in, first out scheduler, where only the highest priority threads will run. The only difference is that instead of relying on a thread voluntarily switching to the next thread, the operating system gives each thread a certain period of time, called a quantum, in which it is allowed to run before it automatically switches to the next thread in the queue. Quantum sizes vary from operating system to operating system, and they also vary based on how the operating system is set up. For example, a desktop PC, it might have a smaller quantum, so then all of the threads feel more responsive, even though they pay more for the context switches, where a server setup might have a longer quantum where it is more resilient. We can see this behaviour where the running thread consumed the quantum and then moved back to the end of the ready queue, resetting its quantum length back to the full length. During a quantum, it might also block, which means that it will stop at its current quantum and then move into the waiting state. This allows other threads to continue executing. However, once it comes back from the waiting state, it can preempt an already running thread and also stopping it mid-quantum, leaving us with two threads, neither of which have consumed their full quantum. For the one that was already running, that we preempted, it will keep how far through its quantum it already was. However, the one that has come back from the waiting state, it potentially has been in the waiting state for longer than one quantum, so the scheduler will reset its quantum back to the full length before it continues executing. Now, let's move on to the Windows scheduler, which is very similar to the round-robin scheduler. One of the key differences is that the Windows scheduler uses priority boosting, which temporarily boosts the priority of higher threads. Priority levels are split into a static and dynamic range. The boosting only happens within the dynamic range, which is also where all of the applications run, while the operating system runs across both ranges. Windows uses a quantum size of about 30 milliseconds for desktops and 180 milliseconds for servers. Each CPU has its own ready queue that is used for threads that have hard affinities. And then there are groups of around 4 CPU cores that each have their own shared ready queues for threads that don't have hard affinities. When a thread is created, it'll automatically be allocated an ideal core to run on. This allocation comes from a round-robin list based on the ideal thread placement for the specific CPU. The ideal core allocated is used as a soft core affinity. For the situation we were seeing before, where a thread may be starved out by higher running threads, Windows includes a generic thread starvation mechanism to handle this as part of the balanced set manager, which is there to do memory-related functions, but has been overloaded with also helping out with thread priorities. The balanced set manager runs at a higher priority than any of the user mode threads that we run. So it will run regardless of how high the priority is of the threads we've created. Every second, it's going to look through the ready queues in batches of 16 threads and trying to find any thread that might not have run for the last 4 seconds. And then it will boost the priority of any of those threads all the way up to the priority of 15, which is the maximum in the dynamic range, along with setting the quantum for that thread to 3 times the normal quantum length. So once it has done boosting, then it will go back to sleep, allowing the rest of the threads to continue. Here we can see each of these threads in the ready queue complete their quantum, and then finally the thread that was at a lower priority completes its larger quantum, which is a lot longer than the ones that were already there. Once its quantum is completed, then it will be put back down to its initial base priority, which was 13. There are many other types of boosts which get applied to different threads, such as boost for foreground windows, boost for I/O operations, such as reading or writing from a socket or a disk, and not all boosts will return back to their initial base priority once a quantum is completed. Some priority boosts will decay over time, which is typically 1 priority level every time the thread finishes its quantum. Quantums are also variable in length, where foreground windows can have quantums that are increased to 3 times their standard length. So instead of a 30 millisecond quantum, you can end up with a 120 millisecond quantum for desktop PCs. It's these variable quantums and dynamic threads that often make Windows feel responsive. The Linux Completely Fair Scheduler, or CFS for short, is the default scheduler used on Linux. Unlike the previous schedulers, where only the highest priority thread is run, it allows all threads to run regardless of priority, but lets the higher priority threads run more frequently and for longer. This is done through the concept of virtual time, of how long a thread has already run. The thread with the lowest virtual time is the one to run next. When a thread is created, it will get a new virtual time that is based on the lowest virtual time of one already in the current CFS queue that it's being added to. The same thing happens when a thread is woken up from a long waiting period. There's also normalization that happens when a thread moves between different CFS queues that are on different CPU cores. Priority is normally done using a concept of niceness, which is how nice that thread is to other threads within the same CFS queue. A thread can be nicer to others by saying that it ran for longer in virtual time, when in real time it didn't run for quite as long. And if it isn't nice, you can do the opposite and say that it didn't run for as long as it actually did. The scheduling period is how long it will take for all threads to have it run at least once within a specific CFS queue. Here is a basic example where we've got 3 equally nice threads. Each will get an equal share of the scheduling period, which for Linux is defaulted to 20 milliseconds. While I've laid out these threads as big blocks next to each other over the scheduling period, there is a reasonable chance that they would have been sliced in between each other during the scheduling period. Additionally, in this example, all of the threads are CPU bound, where in reality we've probably got them blocking and doing all sorts of other operations. If we add another 2 more threads of equal niceness, all threads still get an equal share of the scheduling period, but because there is more threads, they will all get a smaller individual CPU time. Once we start to add niceness in, then we can start to see that the share of time will change. Every time a thread gets nicer, it's consuming roughly 25% less of the time slice than the previous nice level. And the opposite is true for when it is being less nice, where it'll consume 25% more of the time slice. We can scale this all the way up to being as nice as possible, which is a nice level of 19. In this situation, the thread will barely get any time at all, while the remaining threads of equal niceness will get the remaining time shared equally. We can also go all the way to the other end, where it consumes most of the scheduling period, and the threads with the nice level of 0 get barely any time at all. Now let's take a look at the impact of the scheduler on the different parts of our code. Parking is when the operating system puts individual CPU cores to sleep. There are different levels of sleeping, which differ based on different CPU vendors. But as an example, level 1 might turn off the clock for a specific CPU core. Level 2 might flush the L1 caches and put them to sleep. Level 3 might flush the L2 caches and put them to sleep. And then if multiple CPU cores have been put to sleep, then the components that are shared between those might also get put to sleep, such as the L3 caches. Doing this allows the CPU to consume less power and also enables other CPU cores, which are not parked, to potentially boost in their power consumption and run it at even higher than their base frequency. If there is an integrated graphics on the CPU, it can also run faster. So it is a crucial part of both saving power and also increasing the performance of other parts of the CPU. Because it takes a longer time to enter and leave these deeper sleeping states, the operating system can sometimes be reluctant to unpark cores, especially if it is looking at the history of your threads and sees that they're normally just sleeping and not needing much CPU time. Then all of a sudden, you're doing lots of work and consuming more CPU time. It doesn't know how long-lived or short-lived the new CPU usage that you've done might be. One situation where this can occur is if you have a dedicated server which remains idle until a match is ready to play. The operating system might decide to park the majority of the CPU cores to save power. Then suddenly a request comes in to use the dedicated server for a match. It needs to load the content, set up the world for the players, and more. Even though you've given it 8 cores to work with, only one of them might be fully unparked. And it's not until later down the track does the operating system realise that the new load that you're doing isn't temporary and will actually start to unpark the CPU cores. An approach taken to avoid this is typically limiting how deep a CPU core can go to sleep. A scheduling storm can happen when you have one or more threads continuously asking the scheduler to reschedule them by voluntarily yielding. This could be because you are spinning, waiting for a lock to be released, or trying to wait for some length of time to have passed. Here is a small example where on core 1 we have 2 threads yielding, then on core 2 we have 2 threads which are doing actual work. As most of the operating systems have separate queues per CPU core, when each of these threads is yielding, it's not actually looking for threads to run from another CPU core. Instead, it's actually looking for threads to run within its own CPU core's queues, or potentially within shared CPU core queues, similar to what Windows uses. with just a single thread yielding on one core, it's going to be yielding back to itself each time. However, the same can happen when multiple threads on the same core are both doing the yielding to each other. From the perspective of the operating system higher level load balancing, it might not migrate the CPU from the CPU cores, the threads that are on CPU core 2 onto CPU core 1, because it's going to see that the threads on CPU core 1 are both consuming 50% of the CPU time, which is no better than the ones currently on CPU core 2. It is often best to avoid relying on thread yielding. It can vary from scheduler to scheduler for what it will actually do. And in some cases, it might just return back to the current thread, even if there is other work to do, which is of a lower priority, which might unblock the higher priority thread. The thundering herd problem occurs when you have multiple threads all woken up to do the same thing, but only one of them can do the actual work. An example of this is a job system which contains 8 threads. You might submit a single job, but notify all of the threads to wake up because there is work to be done. In this case, all of the threads will wake up and rush to get the job. But if they didn't get the job, then they probably need to go back to sleep. From the perspective of all of those threads, it might not seem like much of an issue. After all, those threads didn't have anything else better to do. However, because trouble with slides. However, because it woke up all of the worker threads, unnecessarily CPU cores might have been woken up, and already running threads could have been preempted. If your job system is lock-free, then potentially increase the cache coherence overheads, slowing down the actual thread which got the job. And if the job system uses locks, then potentially it's causing lock contention, which could lead to other issues like lock convoys, which I'll cover next. Lock convoys occur when multiple threads are all contending for the same lock, but the time both inside and outside of the lock is less than the time consumed by the scheduling around the lock itself when it is under high contention. This is because when a thread could not get a lock, it will tell the operating system that it is waiting to be woken up by another thread. The operating system then needs to find another thread to run while it is waiting, start executing that new thread. Meanwhile, the other thread, when it releases the lock, it must call into the kernel to wake up the thread that is waiting for the lock, causing it to preempt the new thread that was scheduled earlier, and then switch back to the original thread which wants the lock. Because of the scheduler overhead, often people will reach for something like a spin lock. In these situations, however, they come with their own issues, which I'll cover later on. Adaptive locks are often a better alternative to spin locks, as they will both spin and sleep at the appropriate times. However, for lock convoys, this often indicates high contention, and any lock, regardless of how well it spins, the critical section the lock is for still executes in a serial manner. So I feel it's often better to look at the algorithm and code causing the locks to see if there is better ways to coordinate the threads so they are not always in contention, or look at lock-free approaches to the problem. Context switching is when the operating system switches from one thread to another. This could be due to preemption or waiting. There's also context switches that occur between the user mode and kernel mode parts of a thread when it does a system call. Different context switches take different amounts of time, with the most expensive being a context switch that happens between threads in different processes, as they require the TLB cache to be flushed, which deals with virtual address translation. While some context switches are unavoidable, it is often best to look for approaches which minimize context switches. This means looking at non-blocking APIs, which I will cover later, and using an appropriate level of adaptive spinning in the right situations when you know that something you are waiting on will be available within a few CPU cycles. Due to the way in which Windows works with the way in which Windows boosts priority of threads when they are woken up, there is a higher chance of the thread which is being boosted preempting any existing thread which might be running. Priority boosting does not consider how long a thread will remain in the running state for. You might have a thread that gets woken up and only does 100 microseconds worth of work, and then goes back to waiting again. This cycle continues with it being woken up, boosted for the entire lifetime of the thread, meaning that it never actually executes at the base priority that you've given it. For example, you might have a file I/O thread, which you've given a lower priority because you don't want it to interrupt the rest of your threads. However, due to priority boosting, the thread effectively runs at a normal priority because it never runs for more than one quantum when it's woken up. In these cases, you might consider disabling priority boosting for individual threads if you're wanting to work with the explicit thread priorities, instead of letting the priority boosting control the thread's priority. But you also need to consider that this might change things like foreground boosting or thread starvation boosting. Another alternative is to space out priorities enough to compensate for any boosting that a thread might incur. Interrupts are used to stop the current thread that is executing and let the operating system, or more specifically the kernel, handle some event from hardware, another CPU core, or even from the code executing on the current CPU, such as a system call or page fault. The handlers for these interrupts are called interrupt service routines and are designed to be extremely fast because while one interrupt is being handled, typically all of the other interrupts for that specific core are disabled. There can be situations where sometimes hardware behaves in such a way that it ends up sending interrupts extremely frequently, which is called an interrupt storm. Just imagine you have a network adapter, which caused an interrupt to happen every time a packet arrived. This would mean that for every packet that is arriving, potentially one of your threads has to stop doing what it's doing and let the kernel handle the incoming packet, causing your thread to get less work done. The control over interrupt storms is mostly outside of our control, but it can be useful to understand when looking at performance issues. Operating systems use many different techniques to reduce the impact of interrupt storms, such as affinitizing hardware interrupts to single CPU cores, and hardware can also batch interrupts. And there are newer techniques like message signaled interrupts, which are more efficient than the older pin-based interrupts. Some operating systems might also mask off certain interrupts and resort to polling if they notice that interrupt storms are occurring. On any desktop machine, there are probably hundreds of processes running, which combined leads to thousands of threads. Thankfully, most of those threads aren't actually executing all the time, but within those thousands of threads, there might be a few dozen that are doing something at periodic intervals. This could be a watchdog timer checking that threads within that process haven't gotten caught in an infinite loop. It could be a garbage collector running. It could even be polling to check if a file has changed or a registry key has changed, or even if a network packet has arrived. There are a lot of possible things which want to be notified after some period of time has elapsed, or at a set period in time. If each of these timers had 100% accuracy, then you would end up constantly interrupting active threads that are using the CPU, limiting their ability to consume the full quantum before being switched out to a thread which was using some timer or timeout. The operating system can instead group all of them at certain time intervals, for example, 15 milliseconds. So if you request a timeout for 5 milliseconds, you might instead get a timeout for 15 milliseconds. And if you request a timeout for 20 milliseconds, then you might get a timeout instead for 30 milliseconds, allowing the rest of the time to be used for CPU-heavy threads. If you're using any timeout or timer in your game, be prepared for it not to be completely accurate. Some platforms let you have more fine-grained control over this, such as Windows, where you can adjust the timer resolution on a per-process basis using the time begin period function. Priority inversion happens when a lower priority thread is blocking a higher priority thread from succeeding. For example, a low priority thread holds a lock, and a high priority thread attempts to acquire the same lock, but cannot acquire the lock, so it waits for the lock to be released. While it is waiting, there is an unrelated medium priority thread that preempts the lower priority thread holding the lock, which means that the higher priority thread needs to wait for the lower priority thread to be able to execute. In these cases, the higher priority thread has effectively acquired the priority of the lower priority thread that's got the lock. On Windows, priority inversion gets handled using the system I mentioned earlier, which boosts threads within the ready queue that have not run for the last 4 seconds. On POSIX-based systems, there are 2 techniques for this. There's priority inheritance, which raises the priority of the thread holding a lock to a higher priority when another higher priority thread attempts to acquire the same lock. And then there is priority ceilings, where a thread gets raised in priority as soon as it acquires the lock. Neither priority inheritance nor priority ceilings are enabled by default. There are strengths and weaknesses to both approaches. Priority ceilings can result in increased system calls each time a lock is acquired or released. It needs to tell the kernel to raise the priority of that thread. However, this ensures that the work that is done while holding the lock is done at the relevant priority. For priority inheritance, it means that preemption can still occur, but only when it is actually blocking something will it resume the work from where it was preempted previously. Blocking I/O can have a significant impact on performance and I/O throughput when compared to asynchronous I/O. This is especially the case where you're doing lots of I/O operations, such as reading files from disk, reading and writing data from a network, or in many other cases, as it incurs a scheduling cost of being moved into a waiting state and then scheduling a new thread and then being preempted once the interrupt comes back from the I/O device. Then there is the hardware device throughput. Because you only send one request one at a time, there is a big gap between the operating system, while the operating system scheduler is coordinating your threads, so the I/O device is potentially remaining idle. With non-blocking requests, the operating system can more easily create a queue of different requests and send it to the hardware so it can do it in batches. Unfortunately, some operations like opening files still end up being blocking operations because they need to validate if a file exists first. But in these cases, if throughput is important, then you might consider going wide with multiple threads, which might allow for better throughput. This will lead to extra scheduling overhead, but does allow for potentially multiple open requests to occur at once. So it isn't a general solution and very much case by case. Some threads will share more data than others. For example, 2 audio threads might will probably share more data with each other than the audio thread and the physics thread. In a theoretical CPU that has 4 CPU cores, with the first 2 cores sharing the same L3 cache, and another 2 cores sharing another L3 cache. If the 2 audio threads ran on the 2 cores that are sharing the same L3 cache, chances are they would run faster than if they ran on the cores that aren't using the same L3 cache. This is because the 2 threads probably share a lot of the same data and instructions. So when one thread ends up loading something from physical memory, then it's going to be closer as they both share the same caches. Additionally, reading and writing to atomic variables have less steps to go through in order to be visible to both cores. The same can happen at an executable level, where threads within one process are more likely to be sharing data than threads from an unrelated process. Hybrid architectures are where CPUs have multiple cores that are not consistent in frequency or cache layouts. They're becoming more and more common, both within the mobile space and laptops, due to the power-saving advantages they can provide. Especially, they can provide, just a second. This means that they can take advantage of the power-saving advantages they provide, especially when the computer is mostly idle and it can park the higher performance P cores, letting the energy efficient E cores do most of the work. However, this presents an interesting problem. Imagine if your main thread runs on a power efficient E core, then it is probably going to be running slower than if it had run on a high performance P core. but at the same time, it's probably saving battery life of whatever device it's running on if it's plugged into the power, if it's not plugged into the power. If your threads are floating around on any desktop PC, which is normally what you typically want, as you don't know what else is running on the specific computer, then these situations could potentially occur. Intel has introduced the Intel Thread Director, which provides feedback to the operating system with what threads should potentially run on what CPU cores. It specifies different classes for the instruction mix for what it's seeing when the thread is executing. However, if you have something like a job system with a thread pool, then the instruction mix might be varied. It might be doing some network sending in one situation and then a CPU-intensive physics calculation afterwards. So to the thread director, it's not going to see any real consistent load, as it depends on what jobs the thread is actually pulling. So under hard thread affinities, you can specify what CPU cores a thread is allowed to run on with thread affinities. For consoles where the vendor has often specified how their own threads will run on different CPU cores, you can more easily specify thread affinities to ensure that you make full use of the hardware, minimising threads moving around or being preempted. However, once you start to step outside of the console realm and into the desktop realm, it's becoming much less clear what is actually running on the person's computer. Do they have a web browser open with 100 tabs? Are they live streaming the game? Are they playing some music with some complex visualizations happening? If you start specifying hardcore affinities, then you could end up potentially starving your threads or starving other threads, other processors' threads unnecessarily. You don't know how the CPU and memory hierarchies might also be different or possibly change in the future. You might have tested on your PC where you've got the same speed CPU cores all sharing the same last level caches. However, the affinity core numbers that you've used don't consider another CPU which doesn't have the same shared last level caches, has a hybrid CPU, or potentially even multiple different physical CPUs. So spin locks, which I mentioned, I'll get back to. So spin locks are similar to mutexes, except during contention, a mutex will typically put a thread into a blocking wait, whereas a spin lock will loop constantly, checking if a lock has been released. In these loops, it's pretty common to do one of two things: execute the CPU pause instruction to avoid instruction pipelining, and another approach, which is call into the operating system to yield the current time slice, allowing other threads to run, potentially even other threads to run, potentially even the one that has held the lock. In some cases, there will also be a combination of both the pause instruction and yielding to other threads. If you're using the CPU pause instruction only, then the thread holding the lock, and the thread holding the lock is on the same CPU core's ready queue, then you potentially end up waiting for the entire quantum to be given up before that thread holding the lock is able to run and release the lock. If you're using the operating system's thread yield functions, then you're giving up the current thread's quantum and adding it to the back of the ready queue when the lock could have been released a few nanoseconds later. You might be thinking that if it's only for a lock that is going to be over a few instructions, that doing a spin lock is probably going to be the fastest. This isn't really the case with modern mutexes, which are going to be just as fast in the uncontended case. For when there is contention, then potentially the spin lock can be faster, as it doesn't need to deal with the operating system scheduler. But this is only the case if they are a few instructions long, which, because we execute in user mode, we have no control over other things like interrupts, preemption, or anything else the operating system might do outside of our control that could potentially end up executing inside of the lock. So while we might have only had a few instructions, there's potentially a lot more instructions that could end up executing if the operating system decides to do something. So job systems have come in many different shapes and sizes. Many of the things which I've already mentioned can have a direct impact on the design of a job system. If you're using a condition variable, you need to consider what what operations like notify all can do. They could potentially lead to thundering herd problems if there isn't enough work to do. If you're using mutexes, then you could potentially be hitting lock convoys when there is high lock contention. Some kernel wake primitives might involve waking individual threads, and we'll do them in a first in, first out order. This is often done for fairness. So if you're waking individual threads, the one that's woken might have most of its state stale within the CPU caches, where if you had woken the thread that had recently went to sleep, then there's a higher chance of its state being within the CPU caches. Then there is the overhead of doing individual waking. If you submit 10 jobs and then wake threads individually, then you've got a context switch to the kernel each time, followed potentially by an interprocessor interrupt to tell the CPU that it should preempt the current work on a different CPU to run the newly woken worker. And if you're unlucky, then potentially you might have preempted your own thread before it has notified all of the other threads to wake up for the other 9 jobs. If you're splitting work into chunks of equal size as the number of worker threads, then there are no guarantees that they will all start running immediately. You might have some that need to preempt existing threads. Others might have been added to a ready queue waiting for a higher priority thread to run, in which case you are left waiting for longer as one thread was slower to hit its running state. The same thing can also happen if a core is parked and a thread is slow to hit its running state, or if work is being split between performance cores and power efficient cores. There are many more things that need to be taken into consideration when designing a job system to work best with different hardware requirements and operating systems, but that's an entirely another talk. So that's the end. It was a little bit of a mess of all sorts of different things. Are there any questions anyone's got? A lot of the console schedulers are very, like if you've got Windows one that's going to potentially be very similar, and then a lot of them will be based on those POSIX sort of schedulers. They will. Any other questions? I'll take any other questions out in the hallway, I will.
What sort of tools do you use to monitor those
So profilers often have the ability to monitor context switches. That's sort of the main one to monitor. Sometimes they won't include interrupts within that, so you might only get sort of the context switch from one thread to another. So it's really worth not just looking at your own thread's performance, but also look at the individual CPU core. Was it scheduled or was it descheduled during that time? And also include those, if you're making your own profile, include how much was scheduled and how much was not scheduled. Because you don't want to see, oh, this took a millisecond to run, but really it was only scheduled for sort of 50 microseconds. Any other questions? Oh, that's it then, if there's no other questions.